First, I wanted to point out that on Brightspace, I've been posting the lecture notes in the module lecture notes, and recordings for some classes. The recordings haven't been working, but for those classes, I re-recorded the summary. So for every single class, there is a recording now on Brightspace. Those two things. And then regarding homework one, so there were issues with some teams. Not all team members got credit. So if that is the case, send me an email and we'll, right? Now, so now let's start where we left off. What we were doing was we went through table 1.1 and 1.2 from chapter 1, and we need those tables to transform a vector in one coordinate system to another, or to transform a point in one coordinate system to another. And last time what we were doing was we were given a vector in the spherical coordinate system, and we were trying to transform that to the cylindrical coordinate system. We don't have direct transformation equations for cylindrical to spherical or spherical to cylindrical. So when we need to transform from cylindrical to spherical or vice versa, we always transform to rectangular system first. And that's what we're doing here. In this problem 19a, before we can transform this vector given in the spherical system to the cylindrical system, we are trying to transform it to the rectangular coordinate system. And so we got up to this point. These are the three components in the rectangular coordinate system, but the components are not in terms of x, y, and z yet. They are in terms of r, theta, and phi, which are spherical coordinates. So what we need to do is we have to apply the transformation equation for points to convert r, theta, and phi to x, y, and z. For r squared, we have the direct formula. It is x squared plus y squared plus z squared. For cosine theta also, there is a kind of direct formula. It's because what we know is that cosine theta is z by r, and r, we have the formula for that. So these two we can transform easily. What remains is sine theta, sine phi, cosine phi. But we can get those also pretty easily. So what we need to consider is, so we have cosine theta. Now, if we need to find sine theta, just consider a right angled triangle. So, and what we know is cosine theta, right? So cosine theta is, if we consider a right angled triangle with one of the angles being theta, then we can write cosine theta as base over hypotenuse, right? And since the ratio we have is z over that, so that's our base over hypotenuse. Base is z, and hypotenuse would be that. And then, so once you draw this triangle, you can easily see that sine theta would be, it would be the perpendicular over hypotenuse, right? And using the Pythagoras theorem, we can get the length of the remaining side as well, right? This length would be z squared minus x squared minus, x squared plus y squared plus z squared minus z squared, which is, and the square root of that, which gives us x squared plus y squared. So sine theta would be perpendicular over hypotenuse. So in a right angle triangle, if we know one of the angles and either cosine of the angle, sine of the angle, or tangent of the angle, we can get the other things we need from the triangle. So anywhere we see sine theta, we are going to plug in this expression. We also need sine phi and cosine phi. So what we know is we know tangent, right? Tan phi. So we have the formula for tangent phi equals y over x. This is in our formula sheet. And so in this right angle triangle again, so we can call this side, this is the perpendicular, this is the base. So the hypotenuse has to be, using the Pythagoras theorem, square root of x squared plus y squared. And once we know all the sides, we can write sine phi would be y over square root of x squared plus y squared, and cosine of phi would be x over x squared plus y squared. So we have all these expressions in terms of x, y, and z. So we make that substitution, we'll get the components fx, fy, and fz. Now, those components will be in the rectangular coordinate system. And so I'm going to directly write. So once we make those substitutions here, we get fx, fy, fz, and then we plug it back in here to get the vector f in the rectangular coordinate system. So I'll skip the algebra and I'll just copy the final expression. Again, so how did we get that? So in these expressions for fx, fy, and fz, we use these formulas to express everything in terms of x, y, and z. There should be no r, theta, or phi when we are expressing our vector f in the rectangular coordinate system. Okay, so we make those substitutions and simplify to get to this expression. Any question about that? Yep. You could, yeah. That's a good point. So we could leave cosine phi as it is, sine phi as it is. Because our goal is to eventually get to cylindrical coordinate system. So that is just half, right? Half of the solution. Now to get to the cylindrical coordinate system, again, we repeat the same procedure. So we write the general form for the cylindrical coordinate system. So we would write f equals f rho a rho plus f phi a phi plus f z a z, right? And then here we have two unknowns. The unknowns are f rho and f phi. So fz would be the same in the cylindrical and the rectangular coordinate system, so we don't have to get that. And remember, we do the same technique again. So to find f rho, we take f in the rectangular coordinate system, we do the dot product with a rho. That will give us the f rho component, and we have seen computations like that, so I'm not going to do the whole work here. Similarly, to get f phi, what we do is we take f in the rectangular system and do the dot product with a phi. And we're going to have to use table 1.1 to get the dot products between ax, ay, az, and a rho, a phi. So the final answer in the cylindrical system is going to be that. So any question about the process? Okay, if not, so we'll, the final topic in this chapter is differential surfaces and volumes. Okay, so let's consider the cylindrical coordinate system. And in this system, imagine an object, a three-dimensional object, infinitesimal in volume. So very small volume, and it has a range dx in the x direction, dy in the y direction, and dz in the z direction. So a very small volume, which we call differential volume. So imagine an object like that. So that object, so it would be a box, a rectangular box. So in the x direction, okay, so this length is dx. In the y direction, we have dy, and in the z direction, it is dz. What is the volume of this box? Why would it be one? Not a direction, so dx, dy, and dz. Yeah. So this is a very small volume, so we call that differential volume, dv. So it would be the length with height, right? We take the product, dx, dy, dz. So this volume is called differential volume. Now, how many surfaces are enclosing this volume? 6 surfaces, right? And 6 surfaces, but there are 3 types. So first type is a surface that has no variation in x, y, and z values vary. So that would be this. The front would be that type, right? There is no variation in x. The back would also be of that type. No variation in x, variation only in y and z. So we'll call that surface is a differential surface. It's a very small surface. So we write that as ds. And let's call that ds1. So this is an area, and that area is dy times dz. Similarly, the back would also have the area of dy times dz. Then the second type of surface we have is where y is fixed, no variation over y, but variation over x and z. So that would be if we consider the left surface or the right surface. Okay, so we'll call that surface ds2, and that area is dz times dx. And then there is the top and the bottom, right? So the top and the bottom have no variation in z, variation over just x and y. We'll call that surface ds3, differential surface, and dx times dy is the area. Any question? Something that we'll use a lot in this course. That is in the rectangular coordinate system. Now let's try to do the same thing in the cylindrical coordinate system. So our goal in the cylindrical coordinate system is also going to be consider a very small volume, infinitesimal volume, where there is some variation of d rho in the rho direction, d phi in the phi direction, and dz in the z direction. So if I try to make it by hand, so maybe I would start at a point, this point, and then this would be maybe variation over phi, so maybe span of d phi. And then for the variation over z, we could go up or down by dz, something like that. And then we want to show variation over rho as well. So we want to have a difference of d rho. So maybe we would do something like that. So it would be a very small wedge. And so this drawing is not good. So I'm going to copy a nice figure. All right, now let's look at this figure. So in this figure, there is variation over phi. So you see this, it starts at some, let's say this point P, and if this has an angle of phi, this point has an angle of phi plus d phi. So the phi changes if we go from this point to this point, or from this point to this point. There is variation in phi. There is variation in z as well. For example, if we go from this point to this point, say this length is dz. So let's write that down. The height is dz everywhere. And then there is also a range of d rho in the rho direction. So that means if we consider the points on the back side, these points have rho value of, let's say, exactly rho, okay, in the rho direction. And the front points, the front 4 points have a rho value of rho plus d rho. Does that make sense? If we were to write the full coordinates, this point would be, we could call that rho plus d rho, phi plus d phi, z plus dz. Whereas if we consider this point over here, that would be rho phi z. And now this volume also has 6 surfaces. And how many edges are there? I didn't ask that question in the rectangular system, but 12 edges, right? Do we know the lengths of all the edges? Let's find out, okay? So if you look at these vertical ones, those are easy, right? So what is the length of each vertical edge? dz, right? Each vertical one is dz. Then how about this, the radial one? If we go from the back to the front, do we know this radial distance? It has to be d rho, right? Because if we look at this point, it has rho. The first coordinate is rho. This one has rho plus d rho. So that means that this distance has to be d rho. And the same is true for this edge, this edge. There are 4 lines with length of d rho. Now the tough one is the arc. So this arc on the back side, this top arc and the bottom arc, they are equal in length. We can see that, right? It's symmetric. Do we know the length? Yeah. Right. What is the length of an arc in terms of the radius and the angle? So length of an arc would be radius times the subtended angle, right? So that means the radius of this arc is equal to not the radius, the length of this arc is equal to the radius, which is rho. And what is this angle? The subtended angle? Yeah. So if we look at this point, its second coordinate is phi, whereas this has second coordinate of phi plus d phi. So that means when we move from this point to this point, we are making a change of d phi in the phi direction. So this angle, the subtended angle for this arc is d phi. So the length of the arc, we know that as well. Length of this arc is rho d phi. So there are three types of surfaces here as well. So consider the back surface where there is variation over z and there is variation over phi, but no variation over rho. So consider back. And the front surface is also of the same kind. So again, no variation over rho, but over other directions. Now, what is the area of that surface? The back surface. What would be the area? Yeah, this pink one. So because we know the length of the arc now, right? The length of the arc is rho d phi, and now we know the height as well. The height is dz, so the area has to be dz times the length of the arc. So rho d phi times dz. That's one type of area we have. The second type is if you consider the left side or the right side. We'll call that ds2. And this one is easy because the height is dz and this length is d rho. So the area has to be d rho times dz. And then the third type is the top and the bottom. So that would have no variation over, so we have variation over phi and we have variation over rho, but no variation over z. And what would be the area? The blue one supposed to be a rho plus d rho total times d phi. Mm-hmm. Yeah. So if you want to get the total exact arc length, it would actually we'd have to consider the radius of rho plus d rho, right? So, but we'll take an approximation because everything is very small, this differential. So exact length of this arc, although it would be rho plus d rho times, then you do the angle d phi, which is rho d phi plus d rho d phi. So here we are taking multiplication of two differential elements, so that becomes very small. So we can approximate that as just rho d phi. So when we are considering an infinitesimal volume like this, even though the top is not exactly a rectangle, we can consider that as a rectangle. Okay, so let's say it's a rectangle, the top and the bottom both. Now, what would be the area of this? So one side is d rho and one side is rho d phi. So multiplying that, so we have d rho times rho d phi. Any question? So these are differential surfaces. And then similarly, we have a differential volume as well. And so for the volume, we will consider it a rectangular box, even though it's a wedge, a truncated wedge, we'll think of it as a box. So the volume will take the product of the length, width, and height. So what would that be? So we know that height is dz, and the length of the arc is rho d phi, and one of the lengths is d rho. So multiplying those, we get rho d phi dz. So that is the volume of this small box. Any question? Now we're going to look at the spherical system. Okay, so we'll consider the same thing here. We have an infinitesimal volume in this spherical coordinate system, and it has a range of dr in the r direction, d theta in the theta direction, and d phi in the phi direction as well. So what it's saying is, let's say we consider this point. So that point is P. And to get to this point, let me see. This would be the point. So to get to this point, so the difference between this point P and let's call this one Q, the difference in R coordinate would be dr, because this point lies on a sphere of radius r, whereas this lies on a sphere in a different radius, on a different sphere of radius r plus dr. And this point has phi, let's say coordinate is phi, this one will have phi plus d phi, because to get to this point, you have to go around on this circle as well. And then the theta coordinate for this, if this one is theta, this one has theta plus d theta, right? Because to get to this point, you have to go down along this arc as well. So this is a differential volume in the spherical coordinate system. And now let's try to get the lengths of the different sides here. I think first we should number them all. Let's call this one A, B. So one is already P. So the remaining back one, we'll call that C. This one is D, E, and this one is F. Which one is the easiest? So consider the length PA, which will be equal to the length CB, which will also be equal to the length DF. and EQ. The radial lines, there are 4 lines that are equal in length. This one, this one, this one, and this. These 4 are equal, right? So do we know what that length is? It's those lines are along, they are along the radial lines, right? So the change is only in the R direction. So in the inner sphere, the radius is R. In the outer sphere, the radius is R plus dr. So when we move from this point P to A, we're making a change of dr in the R direction. So these lengths are dr. What about an arc like PD? What would be the length of PD? It is d theta. So the variation is over theta, right? When we go from P to D, the variation is over theta. We're going from theta to theta plus d theta, right? But the length cannot be difference in angle. So this is an arc, right? So again, we have to use the formula for the length of the arc. So we know the angle is d theta. What about the radius? The radius is r. The radius for this point P and D, they are both r. So we know the radius is r and the subtended angle is d theta. So we have r times d theta. So that's the second type of length we have. Now consider this one. Either AB or FQ. Or we could consider DE, PC as well. So 4 different ones. So how do we get the length of that arc? What was your answer? R times d phi. So think about it, okay? Can we do R times d phi, or it has to be something else? When we say the variation over phi, it is d phi, right? From when we go from A to B, or we go from F to Q, D to E, or P to C, the variation over phi is d phi. But what is the radius? So think about it. This might need a little bit of thinking. So I'd like you to think about it and find the length of PC. So remember, the point P has coordinates r theta phi, whereas C has r theta phi plus d phi. So can you find the length of the arc PC? To find the length of the arc PC, we need to know the subtended angle as well as the radius. What is the radius? Find the radius. So the answer has to be in terms of r, theta, and phi, right? So I'll write down the options later once you think about it for a few minutes. So that's the first classwork problem. The easiest way to think about it is, so which radius are we talking about, right? There has to be a circle associated with it. So the circle would be this, the circle shown here. That's the radius of that circle is what we're trying to get, because this arc is along that circle, right? So what is the radius? the easiest way to think about it is project that circle or drop that circle onto the XY plane, right? So it lies over here. And project that point P also onto so the circle may be somewhere here on the XY plane, and you project this point P over here. And the projection is, let's say, P1. So what we know is that now this length has to be r sine theta. Why? That has to be r sine theta because this length is r, and this angle, we know by definition that angle is theta. So in the right angled triangle, right? So we have this right angled triangle, and the height, the perpendicular in that right angled triangle, that has to be r sine theta. And that same perpendicular is over here. We're drawing over here. That is r sine theta. So the radius of this circle, it actually depends on where theta is. So the dependence on theta, it is important because if you look at this circle, right, this has one value of theta. This circle is smaller than this bottom circle here. Why? Because the theta value has increased when we get down to this circle. So the radius of the circle is going to be dependent on theta, and that is r sine theta. That is just the length of the arc. And we already know that the subtended angle equals, what is the angle? Difference in the phi coordinate. So that is d phi, right? So the length of this arc, PC, would be, so radius times the angle, r sine theta, d phi. So we know all three types of lengths here. That means we can also now determine the area of each type of surface. For the left side or the right side, let's start there. For the left and right, even though it's not exactly a rectangle, we'll think of every surface, every area as a rectangular. So consider this area now. So we know that one length is dr, and the other length, this length is r d theta. So the area has to be, we'll call that ds1, that would be dr times r d theta. So that's one type of area we get for the spherical system. Then if we look at, so that's left and right. I'll call this front. So A, B, Q, F. So the front and the back. It's hard to decide which one to call front or top. So when I say front, I mean this one. The front and the back. There is variation over phi, and there is variation over theta as well. There is no variation over r. So just phi and r. So ds2 would be r square sine theta d phi. We should write d theta first. D theta d phi. Right? Why? Because one is r d theta and the other one is r sine theta d phi. So multiplying those, we get that area. And then top and bottom. We'll call that ds3. Now this one has variation over r and phi. So r and phi. So we get r sine theta dr d phi. Those are the three types of surfaces. And then also we'll write the differential volume. The volume is, so we multiply all three sides. We get r square sine theta dr d theta d phi. And we're going to see in a bit where we apply these differential surfaces and differential volumes. Any question? Okay, now if you look at your formula sheet, these are the formulas from the first chapter. Now we have covered everything. So the final ones we did, the ones we did today are differential surfaces for the cylindrical system, differential volume, and the same for the spherical system as well. And the rectangular one is quite simple, so we don't need to write that. Okay, so now let's look at problem 22, where we're going to apply those differential surfaces and volumes. So problem 22. So first of all, in your handout, there is a typo in problem 22. Can you fix that? So the surfaces, these are the surfaces. So it might be a little different in your handout. There's a typo. So you should fix that first. Problem 22 and problem 21, they are pretty similar. 21 is for the cylindrical coordinate system, whereas 22 is for the spherical coordinate system. So I'm going to do the spherical one, 22, and you can try 21 at home, and I'll post the solutions on Brightspace. Okay, so first of all, make these changes, note these changes. And for problem 22, since it's the spherical coordinate system, I'm going to copy this figure. Okay, did you note the changes here? So we have a spherical, in the spherical coordinate system, we have a volume that extends from radius r equals 2 to r equals 3. Its range in the theta direction is from 30 degrees to 60 degrees. And in the phi direction, it's from 100 degrees to 130 degrees. So let me write it down. R equals, so it goes from 2 to 3. Theta goes from 30 degrees to 60 degrees. Phi, it varies from 100 degrees to 130 degrees. So this is given. And now what we'd like to find is the volume of this object. So this is not a differential volume anymore. This is a bigger volume, and we'd like to know what the volume is. And we'll also find out, we'll also determine what the areas of the 6 different surfaces are, and we'll find the total surface area. And we're also going to find the length of the 12 edges. Let's start with the volume, right? So in the formula sheet, we have the formula for the volume, right? We have dV equals, this is the formula for the infinitesimal volume. We have dV equals r squared sine theta dr d theta d phi. Now, we don't have a differential object anymore. We have a bigger object, regular object. So to get the volume for this regular object, what we do is we have to integrate the differential volume over r, theta, and phi. So one way to write that integral is, so we can just say volume. Okay, so that means we are integrating in 3 dimensions. It's a triple integral. And so we write r squared sine theta dr d theta d phi. Or we could write it out, we can expand it. So what it actually means is we're writing v equals, so r goes from 2 to 3, phi varies from 30 degrees to 60 degrees. Sorry, we should write theta first. This is phi, and theta varies from 30 degrees the middle one is theta, and the final one is phi, which varies from 100 degrees to 130 degrees. And r squared sine theta dr d theta d phi. So it's a pretty straightforward integral, right? We could even separate it into the product of three integrals. We could write it as phi equals 100 degrees to 130 degrees d phi. And then we have theta equals 30 degrees to 60 degrees sine theta d theta. We have r equals 2 to 3 r squared dr. Now this integral would be r cubed by 3, and the limits are 2 to 3. So we get 27 minus 8 by 3 equals 19 by 3. That's just one part. Now let's look at this middle part. Integrating sine theta, we get negative cosine theta, and the limits are 30 degrees to 60 degrees. So we get cosine of 30 degrees minus cosine of 60 degrees. Question? And can you get the expression for this one, middle one? So you'll have to use your calculator for this one, right? And make sure that you are using it in degrees. You can do it in radians, but just be consistent. Yeah. So all my angles are right now in degrees, so that's why I said put it in degrees. But you could do it in convert to radians. So the first one, the integral over r, that one was pretty straightforward. This one is also, you can do it. If you have your calculator in degrees, you'll get the right answer. But there is one tripping point for this one. So first, do you have an expression for numerical value for the middle one? No, in decimal. So for that integral, we have 130 degrees minus 100, so we have 30 degrees. Okay. Oh, no, yeah, we'll get to that. So can you do this one first? So what do you get when you do it in your calculator? Yeah, that's right. So 0.366, right? Now, what is the first one? this looks like a very easy integral, right? The easiest one probably. Yeah. So what do we do here? We have to convert to radians for this one. You could do the, first you can do the integral in, so you would get, if you do the integral in keeping it in degrees, you just write phi and then you do 100 degrees, 130 degrees, and then the answer would be 30 degrees, right? So we are trying to, our final answer is not an angle that we're looking for, right? We're not asking for an angle. If our final answer was an angle, then it would be okay to leave it like this. But here, what we're doing is we are combining that angle with other expressions. We have to multiply this, this, and this, right? So when that angle is being multiplied with other things or subtracted from or added to other things, you have to convert it to radians. You must. So remember that. So before we combine the three integrals, we convert this to radians. So we're going to write it as 30 times pi by 180 degrees equals pi by 6. And only after that, we can get the volume by multiplying the three things that we have. So we get V equals pi by 6 times 0.366 times 19 by 3. In the middle, it was okay to keep it in degrees because we're getting cosine of the angles. It's okay if we're getting cosines or sines, but for the first one, we have to convert to radians. So multiplying those three will get the volume. Any questions? I have the final number for the volume. If you multiply them, you should get 1.214. Next, any question? You could leave it in fraction. That's also okay.
There's no need to sort of like if our calculator can just solve it once you get the integral step, we can hop directly to the answer. Right?
Yeah. Next, we are going to find see how much time. Surfaces, areas. Okay, so we have three formulas for the surface, right? The differential surface. If you look at the formula sheet for the spherical system, there are three formulas. Now, and we have six surfaces. Okay, for each formula will be used twice. Now we have to figure out which formula goes with which surface. So consider the outer surface first. So let's consider this surface. Okay, so out of the three formulas, which formula should we consider for ds? That's the first question. Right, so let's look at your formula sheet. Right, which one would you pick for ds? For this ds? Can you say that again? To answer that question, so look at the surface and see where is the variation. Okay, there will be variation over two directions, right? So, and so you have to pick the formula that has, d rho, d phi, or dz based on the two variations that you see here. So what are the variations? Which directions? If we look at this surface, is the r changing? Is the radius changing? No, right? Radius is not changing. Phi and theta are changing. So pick the formula that has d phi and d theta. Okay, the one that has d phi and d theta. So that would be r square sine theta d theta d phi. So we have to pick that formula. And once we pick the formula, to get S, let's call that S1. So S1 would be integral of r squared sine theta d phi. And theta varies from 30 degrees to 60 degrees, whereas phi varies from 100 degrees to 130 degrees. And what is that r square? So remember this, we are trying to find the area of this front surface. Okay, so for all the points lying on this surface, what is the r coordinate? It is 3, right? It is 3. And the same, and look at the back surface as well. If you look at this surface, it also has the same thing, right? So when we pick the formula for this, we would pick the one that has variation over phi and theta, but no variation over r. So for this also, we would pick the formula that has d theta and d phi in it, but no dr in it. So for that surface also, we would pick the same formula. But what is different for these two surfaces is that for the first one, we would set r equals 3, but for the second one, we would set r equals 2. And r would be a constant for this integral. Okay, so let's compute this one first. We can integrate r squared first. We get r cubed by 3, and sorry, we don't integrate r squared. R squared is a constant. So we factor that out. And then we integrate sine theta. We get negative cosine theta. And the limits are 30 degrees to 60 degrees. And then we integrate over phi. We get just phi. And that's from 100 degrees to 130 degrees. And remember, r equals 3 for this surface. So we set r equals 3. And then in the middle here, we have cosine 30 degrees minus cosine of 60 degrees. And finally, we have 130 degrees minus 100 degrees. And again, this is area, so our angles cannot remain in degrees here. We have to convert this angle. This has to be converted to radians. So we multiply by pi by 180 degrees. Okay, now if you punch this on your calculator, you'll get 1.7249. Okay, that is S1. Now, this surface, the other one that I mentioned, this is pretty similar. The only difference between the one we just did and this one would be this value, r squared. Instead of setting r equals 3, we would set r equals 2. Okay, so let me do that directly over here. So the only difference is we would have 2 square instead of r 3 square. And the rest could be copied actually. And the answer for this one would be 0.766. Okay, any question? So we did 2 surfaces. There are 4 surfaces left. Right? Now, again, you tell me which formula we should use. If we're looking at the left side, okay, so this left side, there are 3 choices for the formula in our formula sheet. Now, if you look at this left side, left area, what variations do you see? R theta phi. Do you see a change in R? Yes, right? Because we are going along this radial line. So the formula needs to have dr in it. And what else is changing? Theta or phi? Theta is changing, right? We go from this up to down point. Same thing here. So we need to pick a formula that has dr and d theta in it. This is for the left one. The one that has dr and d theta would be this. So we'll call this ds2. And by integrating that, we are going to get S2. So we integrate R from 2 to 3. So we have RdR, and then we integrate over theta. Theta varies from 30 degrees to 60 degrees. And we have just a couple of minutes left. So you can do this integral. This is pretty straightforward. Again, don't forget to change this answer of this integral to radians. So that is the left side. What about the right side? What would be the difference between the left surface and the right surface? Would they be different? So we have to pay attention to symmetry to avoid doing too much work, right? So what we can see is that this left surface and the right surface, even though in the figure it might look a little different, they should exactly be equal, right? So this applies to both left and right. Okay, now 2 surfaces are left, and we'll do that in the next class.